manufacturing processes, there's a lot of things you will not know. So we want to learn DC surfaces, topology, dimensional characteristics in materials processing. Material processing is more general the name. It includes any kind of material manufacturing material, any kind of, as long as there's the material processing, this fall into this category. Okay, so the surface, friction, the friction and the wear parts of the part during subsequent processing when it comes into direct contact with tools, size, and molds, or when it is placed in service. Friction, the surface. Suppose I have a surface, I have a tool, and my tool moves, so the chip will form. So the machine surface will have friction with my tool. So also the chip and my tool, and they will have generated friction. So effectiveness of lubrication and during manufacturing processes, and this is during surface. So we might have the coolant, right? Have you guys ever operated some machines? Did you do something operate the machine, the dry machine, or do you use some coolants or other lubrications? Dry machine, right? I assume, because I cannot see the cooling system. The cooling, especially when you machine the very hard material, titanium, nickel alloys, and because when you machine this kind of material, a lot of heat will generate. So if you do not use the coolant or use this minimum quantity lubrication, and a lot of heat will be there, and your tool will be warm very soon, and there is a very bad heat affected zones on the surface, on the machine surface. It's very bad. So as a result, we need to have coolant. There's a lot of different coolants. We have the fluid coolant, and we have mistake coolant, also minimum quantity coolant lubrication, and we might even use this is a liquid, what do we call? Liquid oxygen, right? We put liquid oxygen there and to cool it. So by the way, the titanium is very difficult to machine. I had the experience when I machined the titanium. The titanium is called fire. It burn. Okay, so this is because of heat. Appearance and the geometric feature of the part and their role in subsequent operations such as plating, coating, welding, soldering, and adhesive bonding, corrosion resistance of the part. So the surface is very important. The appearance. First is the appearance, and also adhesive bonding. So suppose this is machine surface. If we want to bond this material using this surface with other things, and how smooth this one is will affect this quantity of bonding. The corrosion resistance. If the material in machine surface is very smooth, the corrosion resistance will be good. Otherwise, it's bad. So initiation of cracks, definitely, okay, the cracks are closely related to the smoothness of your roughness. We call roughness of your surface. Surface defects, the roughness, scratches, seams, and heat affected zones. And heat affected zones called HAZ. Okay? HAZ because this is a zone because of heat, and there might be some metallurgical phase transformation. So and have an idea of what this one is, so which could lead to the weakening and premature failure by fatigue or other fracture mechanisms. Thermal and electrical conductivity of contacting bodies. So these surveys have so many influence on different aspects. So this surface quality is very important. So this is a metal substrate, the bulk metal. This is Billy, called Billy. Okay, amorphous. You know amorphous, right? Amorphous means that the atoms are arranged in no pattern. Right? So this is called amorphous, consisting of structure that is microcrystalline or amorphous. It develops in some machining and the surface finishing operation, where melting and the surface followed by rapid quenching have been encountered. So here, this is the typical, the cross section of the surface structure of metal. So here, the contaminant at the very top, contaminant, and there might be some absorbed gas, and then these oxide layers. Now here is the belay, okay? Belay is amorphous layer, and here is the work, the hardened layer, okay, of the machine. So here is a metal substrate. This is original structure of this material. Here is this one is the work hardened layer, and the belay oxide absorbed gas and contaminant. So this is just this is empirically and how the dimension, the depth of each of these layers. I want you guys to know with this one. I may give you a problem, ask you guys to label on these different layers for me. So this is the typical metal substrate, the bulk metal, the surface. The surface integrity. So surface integrity, what is the surface integrity? Surface integrity says that not only the geometrical features of surfaces, geometrical feature, but also the mechanical and the metallurgical properties. Okay? So when you machine it, because of excessive heat, some metallurgical properties might be changed already. It's, for example, phase transformation is mechanical. And the characteristics, it influences the fatigue strength, resistance to corrosion, and the surface life. So this is the surface integrity. Surface integrity includes geometrical dimensions, dimensional accuracy, and also mechanical and metallurgical properties of the surface. The surface defects are caused by the defects in original material. You already have defects here. The method by which the surface is produced, okay? And what kind of method you are using, turning, milling, or the laser assisted, or is laser ablation, or these kind of things. And third one is lack of proper control of process parameters resulting in excessive stress and temperature. So this is surface, the defects are usually caused by these three conditions. So major surface defects include cracks, the crack on the surface, and fault, laps, seams, splatter, inclusions, in granular attack, heat effect zone. I remember this one, heat effect zone, metallurgical transformation, plastic deformation, and the residual stress. Residual stress, we know that residual stress, some residual stress is good, some residual stress is bad. Compressive residual stress is good, and tensile residual stress is bad, and for the fatigue life. The surface texture. So here are the guidelines for identifying surface texture. Okay? Texture means geometrical flaws, lay, waviness, and roughness. And the flaws called defects. The random irregularities, especially scratches, cracks, cavities, depression, seams and tears, and inclusions. These are flaws. These are what we call defects. The lay means the directionality, direction. So the direction of the predominant surface pattern and is usually visible to the naked eyes. We don't need to use the microstructure or microscope, and we can see this directionality. So the next one is waviness, a recurrent deviation from a flat surface, much like wave on the surface of the water. So these are waviness, width, and height. How wide it is, how high it is, and this waviness. The last one is roughness. Roughness is, have you guys ever heard of roughness? How smooth and the machine surface is. So this consists of closest spaced regular deviation on a scale smaller than that for waviness, much slow, okay? Waviness and roughness they are very similar, but this is a bigger scale, and roughness is a small scale. Maybe superimposed on wavelength expressed in terms of height, width, and distance on the surface along which it is measured. What I want you to know from this picture slide is that we have 4 flaws, lay, wavelength, and roughness. So they're in terms of surface texture. One question? So surface roughness, and we have 2 commonly used surface roughness. One is called RA, and one is called, this is RQ. Right? So this is the surface. You can see this is our actual surface. So this is a surface profile. This is a digitalized data, and this is a center line. This is a center line. And how can we get this RA and RQ? And RA is YA plus YB, so on and so forth, until YN divided by N. YA and YB, and they are the distance from the point of interest to the center line. You can see? So this is called RA. And be very careful. So this is the distance, okay? This is the distance. The distance is positive. So this is RA. Next one is the RQ. RQ, and they use the square and then square root based on N. So here is, this is the RQ. So some people use RA, some people use RQ here. So based on this slide, I want you to know that we have 2 commonly used roughness quantities, RA and RQ. So this is show us the surface finish. We have flaws. We talk about flaws, lay, wavelength, and roughness. And this is the flaw, right? Flaw is a defect. So this is a wavelength. So this is bigger scale wavelength. So here is the roughness, the small scale. And this is the lay direction, directionality. This is the roughness with the cutoff. So here is surface profile equals arrow from wavelength and roughness. So this is the standard terminology and symbols used to describe surface finish. Are you familiar with this symbol? Everyone, are you familiar with this symbol? Roughness, just like very, very close to the square root sign. So maximum roughness width cutoff, maximum wavelength width here. So this maximum RA, minimum RA, this is a lay. You can just borrow some, this is the picture, some is a drawing from the rig, the machine shop, and you can show this, right? Roughness, so this is roughness of the surface. So this is a lay symbol. So here is a parallel line. Parallel line means that the lay parallel to the line representing the surface to which the symbol is applied. This one is a perpendicular, and lay perpendicular to the line representing the surface to which the symbol is applied across in both directions. The P tape, for turbulent, porous, or particle, or particulate, non-dimensional display. So this is the P tape. Let's go and see different here. This way, perpendicular. This is a cross. This is porous or particular non-dimensional. So status is a peripheralometer. So this is used to measure. This is the surface roughness. To measure the surface roughness with the status. I don't know whether we have in our machine shop we have this one or not. We have this in our machine shop. Oh, okay. So I think we should buy similar things to all the students finish the surveys and then ask them to measure, get more experience. Right? So this is the status. This is very, very sophisticated tool. It's very, very good to measure the profile of the surveys. So then we talk about adhesion. Right? So micro scale adhesion, small scale adhesion. Adhesion means glue come together. So this is the interface of two contacting surveys and show you the real area of contact, here. So this one illustrates the proportion of the parent area and to the real area of contact. The ratio of the area can be as high as 4 to 5 orders of the magnitude. So this is micro weld plastic, this elastic. Micro weld, you mean weld, right? Weld just like weld together. What is weld, guys? Weld means that you metal two materials melt and then you come together, then cool it down, and these two materials become together. So this is micro weld. So if something happens here, it's called cell. This is adhesion. They come together. Micro weld. So friction in manufacturing, and this is a contact. This is not based on this is the laser. Laser machining. There is no friction. And then I'm talking about metal forming or metal this machining. And definitely we have this is the friction. So we have the bending, the deep drawing, sketch forming, and also this metal forming. This normal force is very high. Also, it's a frictional the force, the drawing, rolling, and forging, extrusion. So this is the normal force and during this manufacturing. And usually our model, when we use the Coulomb friction, Coulomb friction equals the mu is defined as the friction force divided by the normal force. If you just go a little bit further, and equals tau divided by the sigma, the shear stress divided by the normal stress. I suppose the area is the same. The Tresca friction, Tresca, I introduced this term to you, right? So when we judge whether this material fails, and we have two criteria, right? The first criteria is called Tresca. Tresca also called the minimum shear stress, right? Sigma 1 minus sigma 3, then take the absolute value. If this absolute value is less than a critical value, it's okay, otherwise it fails. It's called Tresca. Right, second one is called von Mises criteria. Von Mises criteria is more complicated. It is equation. It's an equation there. So this is second time we see the Tresca. Tresca friction is defined as friction factor and divided by this is okay. M is a friction factor. I is the shear strength, right? The strength and stress, they are different, right? The strength is a material parameter. The stress depends upon the geometry load. And this K is shear yield stress of the softer material. So when these two have in common, okay, in contact, these two materials contact. Sorry, this actually use the same symbol. Okay? This is capital K and this lowercase k. I'm talking about the same symbol. Sorry for the misleading. The coefficient of friction in metal forming, metal working. So here is different things. For our case, for me, because I'm a machining guy, okay, and we this is the coefficient, frictional coefficient, and for the tool we commonly use, and also commonly use the materials, OPs. So sheet metal forming is a little bit lower, but machining, you can see for the machining, the coefficient is very, very high. This is for cold. For hot, they don't have this this material. This is data. The profile evolution due to wear. Wear means that this if two objects are contacting each other, so the hardness, because the hardness between them, and the softer one, and we will have some scratch on it. So here is so this is due to the wear. So here this is wear brushed. This is ground surface profile of the wear. See, you can see of the wear is unworn and this is worn material. So this is very different. And there are different kinds of wear. So I want you to pay attention to this slide. I'm very interested. I'm very interested in testing understanding how many mechanisms, how many kinds of wear we have in machining. So adhesive wear, abrasive wear, right? Adhesive wear, as the name suggests, and the adhesive together, and but if you pull one of them, and they will wear. Abrasive caused by a hard and rough surface. Abrasive. Or surface with hard protruding particles bending against another surface. This is abrasive. If I have this is very hard particles on this surface, if I just rub it, and they will scratch them. So this is wear. The corrosive wear because of corrosion, and also fatigue wear. So this is we have four different the wear mechanisms. So adhesive, the wear model. Adhesive, so here is adhesive aspartate contacting. Aspartate is this is called aspartate. So this is adhesion between two asparates. So this is this one and this one adhesion, and we just focus on this circle area and the formation of a wear particle. So see, suppose this is softer, so this is harder, so this is a wear. So this is see, this material supposedly at the very beginning, this material is here, but it comes together with this harder material. So here we will have a crater like this is the feature here. And so this is Archard wear law. They give this law. I will not test your understanding of this one, but I just want to introduce this one. The length of the travel, the normal of the load, and P is indentation hardness of the softer body. So this is the V. So this is how deep the data is. So here is the unlubricated. This is adhesion and other wear adhesion. So here suppose this is a hard material here. This is a hard particle. So if you just drag this one to the right direction, so this hard particle will generate this chip here. So here is a type of wear observed with single die used for hot drawing. This is we have erosion. First one is erosion, heating, thermal fatigue. 3 is thermal fatigue, and 4 is mechanical fatigue, and the 5th one is plastic deformation. So this is in a single die used for hot drawing. This is a die, okay? This is top die, and this is bottom die. So regimes of lubrication. Talk about something about lubrication here. Lubrication. Say suppose we have tooling here, workpiece, and this some lubricant in between. And so this is thick film. Film I mean lubricant film. So this is thin film. It is thin. So this mixed. Somewhere is thick, somewhere is thin. So this is a boundary film. So this is a boundary film. This is the regimes of lubrication generally occurring in the metalworking operations. On surface treatment, is a surface treatment. So if we want to improve the fatigue life of the surface of this component, and there are several ways we can accomplish this goal. First one is short pinion. I told you that short pinion is that we use a gun, but this gun will project this is a tiny particle, metallic particles, and these tiny particles will induce compressive yield stress, compressive residual stress, which is beneficial for the fatigue life. Water jet pinion. Water jet, you use the water, okay? Use the water to induce the compressive stress also. Laser short pinion or called laser pinion, and this is what I introduced to you last time. Use the laser. If the laser interact with this is the workpiece, and there will huge pressure will be generated because of the ionization, and this huge pressure and will induce this compressive yield stress on the surface. And then we have this roller burnishing, cold working. That's the burnish. Roller burnishing is cold working to generate to introduce the compressive yield stress. Explosive hardening use the explosion. Right? So this one is kind of dangerous. Case hardening. I told you the case hardening, right? Can somebody tell me what this case hardening is? I totally forget. Because I'm old. I forget it. Can somebody remind me what is case hardening is? Ben?
When you harden the outside of the material.
Huh?
When you like harden the outside of the material by heating it.
Yeah, can you give me a more complete answer?
Like you said, it's just the outside. The inside can remain soft, but it forms a thin layer of a hardened material instead of doing the entire material.
Yeah. This is correct. It's correct, but I want a more complete answer. And how do we do it? And what is the mechanism to do it? And what benefits you can get? Will you raise your hand first? Maybe you can just Oh.
Hey,
Okay.
it's when you have a case that you put your material in, and it's surrounding material is either a liquid, gas, or a solid, and when heating it, the atoms in the liquid, solid, or gas interact with the material you put in there, and that causes compressive residual stress as a result of it, and it also increases the hardening.
Yes. Right. So this is pretty much very complete. One thing is atom. We use carbon atom because the carbon things are more cheaper, right? Much cheaper. So we use the carbon rich, either liquid or solid or the gas, and to put them together with the workpiece I want to harden. And then I elevate the temperature. After some time, and the carbon atoms will come to the surface of my workpiece. As a result, the hardness will be enhanced and compressive residual stress will be induced. Fatigue life will be better. Okay? So is your answer the same as mine?
Yeah, I was going to say something.
Great. Okay, so as I said, this case hardening, I'm going to test your understanding in our exam. Another one is the thermal screening. Thermal screening is also you can just to improve the surface integrity. And this is talk about roller burnishing. Burnishing is these two guys are rolling together. The first one is a workpiece and the roller, the fillet of the stamped shaft. So this is roller burning fillet of this the shaft. So here is an internal conical surface. I want to treat this surface, right? And the third one is a flat surface. I want to use the roller burning. This is a flat surface. The goal is that I want to improve the fatigue life to induce. This is a cold work. This is thermal wear as radium. So here is the workpiece. Here's oxygen, fuel gas. So this is a high velocity gas. So here is a wear and all rod gas nozzle. This is gas nozzle, this is air cap, the combustion chamber, and this is workpiece. So this deposited coating, you can molten the metal spray. So this deposited coating will be formed on the surface of the workpiece. So this one will, this deposited coating will protect this workpiece. So chemical vapor deposition. So this is surface. Okay, still this related to the surface. So you can deposit something on the surface, some coating on the surface. So here is the carrier gas. This is exhaust. This is vanadium chloride form. So this electro furnace, you need a high temperature. It's a verified shell and the tools are to be coated. So here is the tools. I want to coat this one. And here is the stainless steel distributor. So this exhaust problem. So this is usually how people do the chemical vapor deposition. So the physics department has, so this is the equipment. If you are interested, and you can talk with Dr. Irma K and to use their CVD, the equipment. Dr. Irma K. Have you ever taken the classes? Have you ever taken the physics class? Irma, you know Irma, Dr. Irma K, last name is K. It's a very long name, and just remember K. Okay. She has this CVD equipment. Another one is electroplating. So as the name suggests, electroplating. Also related to surface, I want to make the surface much better. So I have a lot of ions in this solution. Right? So this is a sacrificial anode. So here is the part to be plated. I want to have a plate. I want to plate this bolt. How I do is a sacrificial copper anode. Why this one is called sacrificial? Because as the time goes, so this guy will become smaller until it disappears. Right? Why? Because you have some ion, they become ion. From atom become ion. They will lose these electrons. So they will have from atom become ion. Ion will be in the water. You will be in the solution. So these are heating coils. You want heat to elevate the temperature. You can see the surface is very, very good. So the main purpose for electroplating is that to improve the surface integrity, okay, to make it more beautiful and more to improve the this is particular light. So this is the CMM. CMM is a very, very expensive machine to measure the coordinate measuring machine and with part being measured. So this is very, very expensive. I know the Caterpillar company, and they have one 3 years ago. Yes, almost 3 years. So in April 30th, 2019, I brought my students to the Caterpillar to visit their plant, and we saw, and this is the CMM, the coordinate measuring machine. So to measure the coordinates of your components, right? to see how accurate and the component, the machine component is. Micrometers, and maybe you are familiar with this one, right? So we have several in our downstairs for the mechanics solid lab. So I will not talk about this one. But then talk about dimension tolerance. Dimension and for tolerance. So here's a hole and here's a shaft. So here, this is a maximum diameter and minimum diameter is for the hole. Right? So this is the maximum diameter, minimum diameter. So this is the basic size. This is the basic size of the shaft, minimum diameter and maximum diameter, also basic size. And you can see for the hole and for the shaft, the basic size are the same, right? Just say nominally they have the same size, but because the nature of manufacturing, usually we cannot get very accurate dimension. Do you agree? If you always use some little bit off, the final dimension is always a little bit off than the dimension that we deserve. Why? Because there's always these original errors or some errors introduced. Do you agree? So as a result, the hole and the shaft, when you before you put them together, nominally they have the same size, but actually no. So then it depends on the actual size between them. So we have tolerance. It's a low deviation, this is a low deviation, and this is upper deviation for the tolerance. It's also tolerance for this guy is low deviation, and this is up, this is the deviation. So here, bilateral tolerance means that, okay, so this is my nominal dimension. Then there are two values. This is my upper limit, this is my lower limit. Bilateral tolerance means that these two limits are non-zero. Right? So this is unilateral. Unilateral, you can see this is my nominal dimension. Unilateral means that at least one limit is zero. So this is called unilateral tolerance. So this is a limited dimension. So here, so this is one way, this is another way. So this just put them together. See, this is put them together. The tolerance is taken care of already. But here, this is a nominal. So this is some. The tolerance by processes, different processes, they have different tolerance. Then you can take a look. This is surface roughness. And surface roughness, the lower, the better, okay? The lower, the better. The lower, that means the smoother. Frequency distribution, actually this is about statistical analysis of this is the components. For example, the diameter of the shafts. So usually, nominally, this bunch of shafts, they have the same dimensions, but if you look into it very carefully, no, this is not the case. They have the dimension is bell-shaped. It's a Gaussian distribution. And so this is the diameter of the shaft. We have the frequency of the occurrences, and so this is the this kind of statistical analysis. The control charts are using statistical coordinate control. They have this LC-LX, and they have this UC-LX, and this average of averages. So this you can take a look. I will not test your understanding. The constants for control charts here, and there are several values here, and the sample size. If you want to do the meaningful statistical analysis, the number of samples must be big enough. Otherwise, that statistical analysis it will be very funny. Okay, the number of samples must be big enough.